Hi folks, my name is Dennis Terry. I'm an automotive instructor at the College North Atlantic at the Prince Philip Drive campus here in St. John's, Newfoundland. I currently teach the Advanced Automotive, and in particular, the Advanced Level 4 program, where we teach EVs to the students. Today I'm going to talk to you about electric vehicles and how they charge. There may be some questions surrounding how the EVs, electric vehicles, charge, such as, how do they charge when plugged in? Also, how long does it take to charge? Are there any other factors that will contribute in how long it takes to charge? The intent of this webinar is to answer these questions and to gain some insight in how this is accomplished. As discussed in other webinars by other CNA instructors, there are different types of EVs and different types of battery compositions. But today, I'll be discussing when charging the high voltage lithium-ion battery in particular. Before we start, I just want to identify a few terms that will be referenced during this webinar. Kilowatt, kW, and kilowatt hour, kWh. Kilowatt is a unit of power that describes the rate at which energy is produced or consumed. In EVs, this refers to how much energy the electric motor consumes under acceleration and/or how much energy is recovered during regen and while the high voltage battery is being charged. Kilowatt hour is a unit of energy used over time. In EVs, this denotes the energy storage capacity of the high voltage battery. Comparable to the fuel tank in an ICE, an internal combustion engine vehicle, it indicates the amount of energy the system is capable of storing in the high voltage battery. I want to take a minute and discuss the high voltage battery's range. As I said, the battery will be rated in kilowatt hours, which indicates the total energy storage capacity. On average, an electric vehicle can travel approximately 4 to 6 kilometers for every 1 kilowatt hour of stored energy, depending on factors such as driving conditions, vehicle design, driving habits, even actually the type of tires chosen. This is referred to as efficiency, the higher the kilometers per kilowatt hour, but I just want to discuss charging the high voltage battery, not efficiency at this time. A formula that will help give the maximum potential range is as follows. Using the kilowatt hour of the battery, simply multiply it by either 4, which will give you the low side in range in kilometers, and or by 6, which will give us a potential of our high side, kilometers. If we had a 22 kilowatt hour battery, multiplied by 4, it was a potential range of 88 kilometers. Whereas if we multiply 22 by 6, it will give us another potential range of 132. These numbers will be varied based on factors, but will help when discussing when we charge the high voltage battery. Before I discuss how the vehicle charges, I want to discuss the different levels of charging for EVs and some of the differences associated with each level. The main difference in all levels is the amount of time required to charge the high voltage battery, which requires DC voltage for this to occur. How this happens will be discussed as we go through the presentation. The first level we'll discuss is level 1 charging. Our charging station is simply plugged into a 120 volt outlet, which supplies AC voltage. The charging station typically has an output of 1.4 kilowatts. Also has an output of 12 amps, which will result in around 4 to 6 kilometers of range per hour as we charge our vehicles. Next is level 2 charging. They are supplied with 240 volts AC. They can be hardwired or may have a plug similar to a dryer outlet. They can output anywhere between 3.3 kilowatts to 19.2 kilowatts. They can output as well 16 upwards of 80 amps output, which equates to approximately anywhere between 16 to 90 kilometers of range per hour. Finally, we'll speak about the last one, level 3 charging, known as DCFC, direct current fast charging. The charging station is powered with 400 to 500 volts AC. They can output anywhere between 50 to 350 kilowatts and up, and even a new ultra-fast hard charging stations can be 500 kilowatts, which will be covered in another webinar at a later time. They can output between 100 and 500 amps, but only until the high voltage battery is at 80% state of charge, resulting in around anywhere between 95 and 125 kilometers of range per hour. Just like charging your cell phone with a fast charger, the batteries tend to get hotter with the amount of current entering the battery at such a high rate. The analogy I use in class is pouring a glass of water. As you begin to pour a glass from a pitcher, you pour in rather quickly. As you reach the top of the glass, you need to slow down. Well, this is the case with fast charging stations as well. Once the high voltage battery gets to 80% of charge or state of charge, the amperage level has to decrease. Just like in the glass of water, we have to slow it down. What does all this mean? Well, depending on what level you're charging your EV will influence the amount of time to charge your high voltage battery. There are other factors that need to be taken into consideration that I'll discuss further as we move through this webinar. The charging station and the EVSE are not the battery charger. There is a high voltage component that all plug-in EVs have, which I'll talk about very soon in the next coming slides. EVSE, Electric Vehicle Supply Equipment. This is the connector that plugs into the electric vehicle's charge port. When charging on level 1 and level 2, they simply supply AC voltage to the vehicle. When charging on level 3 or DCFC, it supplies DC voltage directly to the high voltage battery. Remember, the high voltage battery requires DC voltage to charge. There are multiple types of connectors, but in this presentation I'll cover the 4 main found in North America. SAE J1772, the most common connector in North America. It supports level 1 and level 2 charging. As you can see, it's a 5-pin connector. All plug-in EVs have a level 1 and level 2 charge port. Our L1 terminal is when connected to 120 volts AC. It's going to supply AC voltage to our charge connector. Our N terminal or /L2 terminal will act as a neutral when charging on level 1. But when charging on level 2 or connected to 240 volts AC, L1 now is 120 and neutral now becomes a line 2, which supplies an additional 120, and we can get 240 volts AC now supplied to the vehicle's connector. The PE terminal is called protective earth, simply the ground. There are 2 more terminals, which we're going to go a little bit further in depth as we go through, are called CP, control pilot, and PP, the proximity pilot. As I mentioned, we'll speak a little bit further once we get through this presentation. Next, we have CCS, Combined Charging Systems. This is an SAE J1772 connector with 2 additional pins. So in this one, we can still do level 1 charging, level 2 charging, but with the addition of those 2 bottom pins, we can now currently do DCFC. We're still going to have all the same pins in the 5-pin connector as we did previously, but as I mentioned, we're going to have a DC positive, and now we will have a DC negative. So when charging on DCFC, we're only going to be using these 2 pins with the ground to actually charge the high voltage battery, which is going to go directly to the battery itself. Next up, we have Tesla's or /NACS, North American Charging Standard. As you can see, we still have a 5-pin connector. This is going to act identical to the J1772 when charging on level 1 and on level 2. But as you can see, in the L1 and L2 pins, we now have DCFC charging, all within one connector. We didn't have to add the 2 additional pins down bottom. So our pins are still going to represent the same thing, but to the addition, instead of just only having an L1, now we have a DC positive. And over on our L2, now we have a DC negative. We're still going to have our protected earth or a ground, and we're still going to use our control pilot and our proximity pilot to charge. Lastly, we're going to talk about CHAdeMo. I'm not going to go into details of all the individual pins as you can see above and below, but this one is only going to be used for our level 3 DCFC charging. We're still going to have our control pilot and our proximity and our main ground, but the main premise of this connector is going to be for DCFC. And this is only going to be found in a couple of manufacturers today. So let's recap See what we've learned so far. Kilowatt is a unit of power that describes the rate at which energy is produced or consumed. Based on the level of the charging station, will be dependent on the output of what kilowatt it will output when an EV is plugged in. The charging station and the EVSE are not the charger. They are simply a way to supply either AC or DC voltage to the charge board, depending on what level charging station we're connected to. Kilowatt hour is a unit of energy used over time. High voltage batteries are rated in kilowatt hours, the amount of electrical energy storage. And as we said, it requires DC voltage to be recharged. So what are we missing? What actually happens when I plug in? When you connect the EVSE to the charge port, if connected to a functioning charging station, two things occur first. The proximity pilot and the control pilot both play a significant role whether or not an EV charges and at what rate it will charge at. Let's talk about the proximity pilot first. It signals to the EV that the EVSE is actually connected. It also prevents the vehicle from being driven away while connected to a charging station. The control pilot is a handshake between the charging station and the EV. It negotiates the maximum amount of charge that can be accepted. It monitors charging for faults. It also allows charging of the high voltage battery to commence. The onboard charger, OBC, or also known as an AC/DC converter. It's only used when charging has commenced. It's also only used during level 1 and level 2 charging. It's not used during DCFC. During DCFC, it flows directly to the high voltage battery, bypassing the onboard charger. The onboard charger uses supplied AC voltage from the charging station and converts it into high levels of DC voltage in order to recharge the high voltage battery. The charge port is directly connected to the onboard charger. The onboard charger connects directly to the high voltage battery. The onboard charger is also going to require cooling. Converting these high levels of voltage will generate heat. It's going to be associated with the amperage to create our heat. They can be mounted in many different places depending on manufacturer. And they're also going to have high voltage cables that are going to be attached from the charge port to itself and then from the charger down to the high voltage battery. Factors that control the amount of time to charge. The onboard charger has its limitations. This is referred to as the acceptance rate. This means the maximum amount of kilowatts it can accept. The level of the charging station will dictate the amount of kilowatt output, also with the amperage. The onboard charger must decipher how much that station can output and how much of that it can accept. Scenario 1 is a vehicle has an acceptance rate of 3.3 kilowatts on the onboard charger, connected to a level 1 charging station with an output of 1.4 kilowatts. And we're also going to use for this example and all the others that the high voltage battery will have a rating of 22 kilowatt hours. So what do we do with that information? Let's break it down. Based on the information provided to obtain the amount of time required to charge the high voltage battery, the following must be calculated. Using the size of the battery in kilowatt hours, we need to divide the output of the charging station to give us the time to charge. This is directly influenced by the acceptance rate of the onboard charger. If the onboard charger has a lower acceptance rate than the charging station, the EV can only accept a kilowatt rating of the onboard charger's limitations. The example we will use, previously we had a 22 kilowatt hour battery. The acceptance rate of the onboard charger was 1.4 kilowatts. So if we take 22 divided by 1.4, that's going to give us an astonishing rate of 15.7 hours to recharge our high voltage battery to 100%, which is quite an extensive amount of time. Scenario 2. A vehicle has an acceptance rate of 1.4 kilowatts. This time we'll be connected to a level 2 charging station with an output of 19 kilowatts. The high voltage battery will still have the same 22 kilowatt hour rating. So this time the onboard charger has a 1.4 kilowatt rating again, but the charging station outputs 19 kilowatts. The onboard charger can only handle 1.4, so the times are going to be the same. The onboard charger's acceptance rate is a deciding factor when charging on level 1 or level 2, even if the output of the charging station is higher. So we can still use the same calculation of 22 kilowatt hour rating battery, divide that by our 1.4 acceptance rate of our onboard charger. Even though the charging station can output 19, it's still going to give us an astonishing rate of 15.7 hours to charge a high voltage battery again. Scenario 3. A vehicle now, we're going to up the rating of the onboard charger to 6.6 kilowatts. We'll connect to a level 2 charging station with an output of 19 kilowatts. We'll still reuse the same high voltage battery of a 22 kilowatt hour rating. So as we stated, the onboard charger has an acceptance rate of 6.6 kilowatts. The charging station outputs 19 kilowatts. So let's see the difference this time. Now let's do the math and see what happens. If we take our 22 kilowatt hour rating battery, divide it by our 6.6 acceptance rate of our onboard charger, even though we have an output of 19, we can still only accept 6.6. So if we take 22 divided by 6.6, now our charging times have significantly decreased. As we can see, it is now only going to take 3.3 hours to recharge the high voltage battery, which is quite a difference from our level 1 charging. Scenario 4. This time the vehicle onboard charger is going to have an acceptance rate of 19 kilowatts. We'll connect to a level 2 charging station with an output of 19 kilowatts while still utilizing our 22 kilowatt hour rating battery. So this time our onboard charger now has a significantly higher acceptance rate of 19 kilowatts, and our charging station can output 19 kilowatts. So the vehicle now is 22 kilowatt hour battery. We can take that and divide it by our 19 kilowatts input, along with our 19 kilowatt acceptance rate, and we will divide those numbers, and as we can see, now we can get quite a different time. As we can see, we've decreased our time significantly again to 1.15 hours to charge a high voltage battery. So it should be clear now what controls the amount of time it takes to charge a high voltage battery. All these factors will directly impact the charging times: the size of the battery in kilowatt hours, the rate of the onboard charger, and the output of the charging station. But there still may be another deciding factor which may influence this as well. Let's stay tuned and see. So that's a wrap, or is it? Does anything else affect how long to charge? Yes, it does. Temperature. Temperature plays a crucial role in how long a high voltage battery takes to charge. Just like how we move slower on a cold day compared to a warm one, high voltage batteries behave the same way. When the battery is cold, it takes longer to charge and provides less available range. This happens because the electrolyte inside the battery becomes thicker, slowing down the movement of positive and negative ions. With slower ion flow, charging takes more time. On the other hand, high voltage batteries also don't like to be subjected to high levels of heat. Excessive heat speeds up chemical reactions inside the battery, which leads to battery degradation, damage over time. High voltage batteries perform best when between temperatures of 15 to 35 degrees Celsius, where the internal chemistry is most efficient and the charging times are the fastest. Wrapping things up, factors that influence the amount of time it takes to charge a high voltage battery as a recap. Number one is definitely going to be the size of the high voltage battery in kilowatt hours. The larger the kilowatt hour rating, the longer it can take. The acceptance rate of the onboard charger in kilowatts. depending on our onboard charger's acceptance rate, is how much kilowatts of that output the station can provide to us that it can accept. The level of the charging station, whether we're on AC or DC voltage, meaning if we're on level 1 or level 2 for AC, or if we're on DC-FC for level 3 charging. The output of the charging station in kilowatts. Also, as we just discussed, the temperature of the high voltage battery. All of these factors are going to dictate the amount of time it takes to charge a high voltage battery. So we have a lot of factors to take into consideration, but if we simply use the voltage or the kilowatt hour rating of our battery, our acceptance rate of our onboard charger, the output of our charging station in kilowatts, we can do the math and simply say, based on a perfect world, perfect temperatures, it would take the amount of time by dividing the kilowatt hours by the output and the acceptance rate of the onboard charger. As we mentioned, temperature is going to play a crucial role in this, whether it's cold or hotter, is going to directly influence this factor. Thanks for listening, folks. Hopefully you've gained some insight into how EVs charge. And hopefully I've answered some of the questions you may have had in regard to this topic. We look forward to future webinars. This is an ever-changing field with constantly updated topics. I'd like to thank RBC Foundation and CNA for allowing me for this opportunity to speak with you today. CNA are currently in the process of developing a charging station installation course. If you'd like to seek out any more information, please contact CNA in your local area. I'd like to thank you all for taking the time of listening. Again, my name is Dennis Thierry. I'm an automotive instructor at Prince Philip Drive Campus, CNA. Have a great day.